I want you to picture this. You're driving home on a scorching summer day. The sun is beating down, the air shimmering with heat. You glance out your window at the roads stretching ahead, jet black asphalt rippling in waves from the heat. And then you notice something. The road is absorbing all that heat. It's radiating warmth like a giant oven. You can literally see the heat rising off it. Meanwhile, the white lines painted on that same road? Cool to the touch. White buildings beside the highway? Noticeably cooler. Even your white car stays cooler than a black one. So here's the question that should bother you. If black absorbs heat, and white reflects it, why on earth are our roads black? Wouldn't white roads be cooler, safer, and save us from turning every street into a frying pan? But here's the surprising truth. Roads aren't black by accident. They're black because of a century-old discovery that changed transportation forever. Today, we're uncovering why roads are black instead of white, how a sticky byproduct became the foundation of modern travel, and why changing the color would actually create more problems than it solves. To understand why roads are black, we first have to look at the nightmare of early road travel. Picture America in the early 1900s. You didn't have smooth highways, you had dirt roads, and dirt roads were absolutely brutal. When it rained, mud pits that swallowed wagon wheels and early cars whole. When it was dry, clouds of choking dust that covered everything. Roads developed ruts so deep, horses broke legs. Cars got stuck constantly. Traveling just 20 miles could take an entire day. Cities tried everything. Crushed stone, wooden planks, bricks, concrete. But stone roads were rough and loud. Wooden roads rotted. Bricks were expensive and shifted. Concrete was better, but it cracked in extreme temperatures and cost a fortune. Then someone had a wild idea. What if we used the black, sticky waste product from oil refineries, something they were literally throwing away, and mixed it with rocks? That black waste product was asphalt, and it changed everything for 3 brilliant reasons. First, the glue. Asphalt is basically nature's superglue. When heated, it becomes liquid. When it cools, it hardens into a flexible, waterproof surface that binds rocks together into a solid mat. Think of it like this. Imagine trying to build a wall with dry stones versus stones held together with strong adhesive. The glued stones stay put. They don't shift. They don't separate. That's what asphalt does. It creates a smooth, unified surface that can handle tons of weight without falling apart. And because it's flexible, it doesn't crack like concrete when the ground shifts or temperatures change. So why is it black? Because asphalt is made from the heaviest, darkest components of crude oil, basically what's left over after you extract gasoline and diesel. It's black because of its chemical composition, thick, carbon-rich hydrocarbons. Second, the money angle. Here's where economics comes in. Asphalt was initially a waste product. Oil refineries had mountains of this stuff they didn't know what to do with. Using it for roads meant it was dirt cheap. Even today, asphalt roads cost about 30 to 40% less than concrete roads. They're faster to lay down. An asphalt road can be ready in 24 hours. Concrete takes a week, and when asphalt roads need repair, you can patch them quickly and cheaply. That black color is literally the color of cost savings. Every major highway system in the world runs on asphalt, because countries simply couldn't afford to build millions of miles of concrete roads. So if black absorbs heat, why don't we paint roads white? Good question. Cities have actually tried this. Los Angeles painted some roads with white reflective coating to combat urban heat islands. And it works. Sort of. White roads do stay cooler, up to 10 to 15 degrees cooler than black asphalt. But here's the problem. That white coating wears off fast. From tires, weather, oil spills, dirt. Within a year, you're repainting. That's expensive and disruptive. Plus, white roads create glare, blinding reflections that cause accidents. In hot climates, the glare becomes a safety hazard. Drivers literally can't see clearly. And here's the kicker. White roads don't melt ice and snow. Black asphalt absorbs heat, which helps melt snow faster in winter. White roads stay icy longer, creating dangerous driving conditions in cold climates. The black color is actually a feature, not a bug. Now, engineers are developing lighter colored asphalts using different aggregates and binders. These cool pavements are tan or gray instead of black. They reflect more heat, but still maintain asphalt's structural benefits. Some cities are testing pervious concrete in parking lots. It's lighter colored and lets water drain through, but it's still too expensive and maintenance-heavy for highways. The reality: black asphalt dominates because it's the perfect balance of cost, durability, and performance. Every alternative either costs too much, wears out too fast, or creates new safety problems. That black road isn't a design flaw. It's a calculated engineering compromise that served us for over a century. So next time you're driving on a black road, don't just see a hot surface. See a marvel of accidental engineering, a waste product transformed into the backbone of modern civilization. See a material so cheap and effective that we've paved over 4 million miles of America with it. See the reason you can drive cross-country in days instead of weeks. That black ribbon of road, it's not just asphalt. It's the color of progress. If this changed how you see everyday roads, hit that like button and subscribe for more surprising histories hiding in plain sight. And drop a comment. What other simple thing should we investigate next?